so the DNS protocol was invented many years ago when people didn't try to abuse the DNS. They didn't abuse the internet. They didn't try to trick people. They tried to play nice. But the protocol assumed basically that the answers it got back to every question it got were the right answer, the correct or the legitimate answer, whether or not it was a mistake at the other end, but it came from the right source. That was very important. A long time ago, it was discovered that this is a bad idea. People will try to lie. And so DNSSEC came across, DNS security extensions came across, and added to the DNS a layer of security which was based on cryptography and digital signatures and checking, so you can validate, you can make sure the answer you get back came from the right source. And that was the start of why we have to think about cryptography in the sense of the DNS. Now, people use the DNS, the people that will be involved with this, anyone who uses the DNS basically gets their answers from recursive servers. Operators run recursive servers, whether an ISP will run recursive servers because they do that as a service for their customers. Anyone at home will just look things up, not thinking about the default server they use. Or it could be providers of services within an organization, a large company, a large enterprise, who does it for the college campus, for the company they're in, and whatever. Those folks also run these recursive servers, and both of these recursive servers, they're the gullible elements. That's what we're trying to protect. So these can be run in a very gullible manner, just saying, give me whatever you get, or they can participate in security. And the first thing they need to do to add security to the DNS is they need to have something called a trust anchor. They need to know what to place their trust. It's like if in daily life, if you do anything, you trust something. You trust this bank, you trust this store, you trust where you live, you trust your relatives. And from there you may learn other things. You may trust your friends' recommendations to go to a store, for example. So the trust anchor is important. It's very personal to the operator. It's their idea of trust. And they have to base it on something. And in DNSSEC, it's going to be a cryptographic key, a public key. So the public key that's involved here is called a KSK, the root zone KSK. ICANN is operating the root zone KSK. There's also a thing called a ZSK that's operated by VeriSign, and VeriSign and ICANN work together to manage all the DNSSEC of the root zone. And this is the source for anyone trying to validate the DNS. If you take the KSK from ICANN and you install it in your machine, you do it correctly, and it's the right one, and everything's perfectly done, you'll be able to validate that answers to the DNS are coming back exactly as they should from wherever they're coming. The ICANN KSK doesn't sign everything. It only signs the start of a tree or a hierarchy of all of the trust that's out there. So it scales really well, but it's a very important parameter. And ICANN has been signing with the KSK for somewhere around 6 or 7 years, and it's worked. We haven't had problems with that key. There have been problems in DNSSEC down in the tree as people have done operations. We've learned how not to do things. We've learned how to do things correctly too. But this key that's been put in there was installed in about 2010, and it has never been changed. Now, in that time, the key has been operating on our end. We sign data with it. And people outside of ICANN have gotten a copy of this key in some manner, whether it's in the software, whether it's from a website, whether they get it from the DNS. Somehow they get that key and they can install it in their own systems that ICANN has we don't even know who they are. Anyone can do this. No one makes a list of this. Nobody knows any idea who has all of this. So this is basically ICANN saying we're going to change something at our end, and everyone out there who's used this has to do the same. The problem is we don't know who everyone is. It's a very large thing. There's no roster. There's no governing who's been involved in this over the years. So when we make this change, it's a very small change to make. We're going to change a cryptographic key with a few key commands, but everyone else has to get the results of that into their computers to keep working. If they don't, they could have they could stop getting data from the internet. They could stop connecting to names on the internet. They wouldn't get anything coming back through the security system. They'd have to revert either to being unsecure, or they would go nowhere. So this is why the changing this one key on one end is such a simple thing, but has such a large repercussion.